I'm making circuit boards from scratch. As I suspect a lot of you are able to empathize with, back in August, after one of the patrons, Gert, who you'll see in coming videos, came down to help me work on the boat, it was a heat wave. And I thought, instead of working on the boat where I'm exhausted, maybe I'll just start working on the circuit board, wait for the heat wave to pass, and then go back to working on the boat. That was in August. It's now November 3rd, as I sit here and record this. I wanted to start developing the compass rose, and I have some pictures I'm going to show here. I don't think I took any video of some 3D models I printed and made. And then I thought, okay, well, I've got everything ready. I'm ready to start programming them. I had my Charlieplexer board. I even made up a little distribution board. It's not anodes and cathodes because they can switch their roles with Charlieplexing, but I have 2 banks of 9. This little board and this little board was going to let me run all of these to the various LEDs. And I thought, how am I going to get into it? I'm going to start programming, and I'll make a video and show the process of learning how to write software for Charlieplexer. Charlieplexer is just a way of driving a whole lot of LEDs. Very, very quickly, I realized that was not feasible. I was placing all the wires, another picture here, and they just weren't holding on to the pins of the LEDs. If I even bumped them slightly, the wires would fall off, and I had 144 LEDs. So what was that, 288 wires I was gonna have to run back to the circuit board. It's just, no, it wasn't gonna work. I was gonna make a circuit board whose sole purpose was to run those 18 wires in a circle and bring them back to a header that I could bring out to the STM. It's one of the reasons I bought these Nucleo boards. Actually, this one in particular, because it has a CANbus adapter, which I'm going to use for the NMEA 2000 connector. And I thought I could start learning this. Anyone who works in IT is very familiar with the risk of feature creep. And oh lordy, did I hit some feature creep. The first board I was going to develop is the Compass Rose board. And then talking to folks, especially on the Patreon, I cannot tell you how unbelievably amazing the help has been on the Patreon. Before I start showing you the boards that I'm building, let me first say that all of the good in them comes from the community. What I had started out with versus what I have now, it blows my mind. Yeah, I can't say thank you to my patrons enough. I mean, there's the financial support, of course, but more than that, the tech support. I actually created a channel in the Discord called Tech Support. Has been phenomenal, and there's so many brilliant people there. If you've ever thought about joining the Patreon, not even for me, just to be able to chat with these amazing people, the stuff they talk about just over my head, it's amazing. Anyways, so I'm going to start off by showing you, it was literally just going to be the IS31FL3731 Charlieplexer chip. So here you can see the 9 A channels and the 9 B channels. And then they go out to the ring of LEDs. And that was it. That's all I planned to have. And then I thought, okay, you know what? If I've gotten this far, why don't I add one of the LCDs? You can see in the middle of the 3D print, there's going to be there's a slot for one of the LCDs. One of these. I've probably mentioned it before, but briefly, everything that I'm putting on the board has it's red light with an LED wavelength of 625 nanometers or higher, which specifically I chose because it doesn't trigger the messing up your night vision and the cones on your retina. Anyways, so I thought, okay, well, you know what? I'm going to add the LCD. Great, did that. That was it. I had a little dip switch because I was going to switch. At the point here, I didn't know if I was going to use 3.3 volts or 5 volts to drive it. Doesn't matter. And that was it. That was it. That was going to be the whole thing. So you can see here, it was just a ring of all of the LEDs. It had the LCD, it had a pin header here, and then just some resistors and stuff. And the actual, I said IS, I said the model number wrong earlier. It was the IS31FL3731. And that was it. That's all I was going to do. And the supporting capacitors. That I had probably within a week. And that was my goal. But then folks said, well, if you're doing this anyway, why don't you put the STM32 on there as well? And that started a chain reaction. That board went from that has become this. Now, the first thing I did was I added the STM32, and it was going to run the connection to the IS31 right here. So that much stayed the same, and I still had the LCD. Since then I've decided I'm just going 5 volts. So the stuff you saw before with the 3.3 volts, it's gone. But once I had the MCU on there, I thought, well, how am I going to flash it? Because these boards have a USB header on it. It has the ST-Link programmer on it. It's a thing. Not really relevant, but I knew I had to replicate it. And so I ended up creating this little jumper header, which is the single wire programmer. I don't actually even know how this works yet. I'm getting an external programmer for it. More of that later. So I added that, and then I thought, well, if I've gone this far, why don't I put an NMEA 2000 connector on it? And then that way I can actually pull the power, because I'm building NMEA 2000 into the boat, which I have started, but it has not turned into a video yet. So I did that, and I had the CAN wires going straight to the CAN pins, the N2K TX and RX, and that was fine. And then someone was like, you really want to isolate the boat from the control logic. Very similar to how you have to protect against galvanic corrosion on the boat, you want kind of the same idea. You want to separate the grounds, have galvanic isolation between the boat and the circuitry on the motherboard. I'm calling it a motherboard, the PCB I'm making. So with that, I realized I had to add in an isolation CAN transceiver. I cannot stress to you, 3 months ago, when I thought, I'm going to spend a week or so to make a PCB. How hard could it be? I didn't know any of this stuff. The last 3 months has been one of the most intense learning curves I have been on in this entire project. I'm trying my best to not make this video too rambly and just get to the meat of it. But good Lord, there's so much in my head right now. Anyways, so the CAN isolator allows for the data to go from the NMEA bus to the internal logic without having any actual electrical connections. All of the stuff that you see here is now up on the GitHub, link in the description. I am releasing everything I'm doing. The PCBs are going to be under Creative Commons, ShareAlike, Attribution-NonCommercial version 4. It's printed on the circuit boards. The firmware is all going to be a GPIO v3. There's no way I could try to keep this private, given how much amazing help I've had from outside people. The community has built this as much as I have, so whatever value others might find into it, it's now up there on GitHub. I'm bouncing all over the place. I hope this is not a unfollowable video. Here's my bill of materials, the BOM, something else I've had to learn recently. The bill of materials for all of the parts. Oh, that's just for the MCU, for the main control unit, different kind of MCU. This is a unified part, so all of the parts that I'm using on all 4 of these boards are here, and I have a listing of which board uses which parts and how many boards I want to build and blah, blah, blah. And it includes all of the data sheets. So you nerds who are watching this, if you're curious about anything in particular I've chosen, there it is. Now, so getting back to this. So it's got the CAN isolation, but then I have to have a way to power this chip, which I've got 12 volts coming in from the NMEA 2000 bus, which could actually be between, say, 10 and 16 volts because it's coming off the boat and boat voltage is not stable. Now, actually, I say that, and that's not entirely true. Where are you? Hello? I have a bunch of power supplies that I'm going to be putting on the boat. This one is 48 volt to 12 volt. That's might be how I drive the NMEA 2000. I also have a 12 volt to 12 volt. The point is that I'm going to have the NMEA 2000 bus powered by a DC-DC converter, whether it's 12 to 12 or 48 to 12. That means that regardless of what the battery voltage is doing, the output voltage is stable. Think about when you're charging your batteries, what voltage is coming off your alternator if you still have a gasoline engine? If you're using an external charger like one of the Victron units I'm using, what voltage is it putting it onto the bus in order to charge it? That's what all of this stuff sees, unless you have a DC-DC converter. Right, so in order to deal with that, I had to have a 12 volt to 5 volt. There's buck converters, there's linear something or others, I'm forgetting the name of, linear regulators. There's different ways of changing the voltages. So I've got one that goes 12 volt to 5 volt, non-isolated, and that 5 volt powers the ship side of the NMEA 2000 CANbus transceiver. But then on the other side, I have to be able to power the isolated side, but I can't do it from the same supply because that would break the whole point of having isolation. So to do that, I have to have Where is it? Where is it? Where is it? Hello, hello, hello. There we go. I have a 12 volt to 5 volt isolated, and that 5 volt then gets adapted from 5 volt to 3.3 volt. So this 5 volt rail and the 3.3 volt rail are isolated from the power coming in from the boat, and it's the 3.3 volt side that powers the isolated side of the CANbus transceiver. Now, one of the things I'm sure I've mentioned multiple times by now is that I want this to have a very 1980s feel. So as much as possible, partly to cheat because I want to hand solder all of this and I'm not very good at soldering yet, bigger components are easier to solder. But I also wanted to go for the 80s aesthetic, so as much as possible, can you see that? I'm using old-fashioned through-hole parts. I come from an IT world where I use RS-232 serial connections all the time to configure switches and UPSs and PDUs and blah, blah, blah. So I'm very familiar with, in the Windows world, you'd probably call it Telnet to port 25. I want you to be able to do the same thing on these boards. So you can take a standard serial adapter. Oh, I even have one here. Lordy, I need to clean up. There it is. So anybody who works in IT is familiar with one of these doohickeys. So that's an old-fashioned DB9 to USB adapter, and if you're running in the Windows world, when you plug this in, you get a COM port. Fellow people from the 80s and 90s are very familiar with COM ports. Dev TTY USB blah, or ACM blah for the Linux people and for the Apple people. That'll allow you to be able to see what's happening on the controller from a terminal session, which just tickles me pink. So that's what that's for. So that's the MAX 323. That gives me the serial connection into the MCU. And the MCU I'm using for most of these boards, not for the main one, but for most of them, is the STM32 C0 Charlie 0 92 KCT, Kilo Charlie Tango 6. It's a relatively lightweight, but it has a built-in CAN transceiver, FD CAN specifically. Not that I need FD CAN because NMEA 2000 is 250 kbps, but it's backwards compatible. Blah, blah, blah. I'm putting memory on these. And to tickle my sysadmin nerve, I'm doing RAID level 1. Not actually RAID, but it's the same concept. I'm putting two 64 kilobyte EEPROMs, these things. They're so small. These scare me. See how tiny they are? They're absolutely minuscule. Part of this learning curve is I'm gonna have to get a lot better at soldering. Right now I do not have the skills to put those on, but if you're gonna learn something, jump in the deep end, right? The idea behind these, each one of these will have a different purpose. And I don't even know if I'm gonna use them, but they're relatively cheap, so I'm putting two of them on all of the boards. It's basically like a tiny wee little baby hard drive that can go on each of the circuit boards. I can write something to that, and it's there if the system power cycles. And these connect over something called I2C, which is a communications protocol that I'm using all over the place. It's kind of like, again, for the computer people, sort of how you have a PCI bus, or if you're really old, remember the old ISA buses. Each device on the bus has its own address, and then the MCU can just put a message out onto the bus and say, here's something I want you to do or write, and or give me some data, or I want to read some data, and it comes and goes over the I2C bus. I had originally thought I was going to use, it kills me. I made all of these handmade PCBs, and now I'm not going to use any of them. So SPI, I don't remember what it stands for, but this was going to be how I was going to drive all the LEDs before I decided to switch to a multiplexer, a Charlieplexer. Anyways, point is, it's a bus. I can string a whole bunch of devices off of it, and it only needs a couple of GPIO pins. One of the things I've learned very quickly is how fast you run out of general purpose input-output pins on these little MCUs. Being pin-wise is something you really have to be careful of when you're designing this stuff. Okay, what's next? This is very, very simple. Some of these parts here are diodes that have been crossed out because I'm not quite sure what's going to be the best way to protect the data going to and from the GPIO pins that come off the circuit board. What do I mean by that? So for each one of these, if you saw my earlier videos when I was building these on breadboards, which was a whole mess, I had a switch to allow me to change what's displayed on each one of these. So I have like a momentary contact up and down switch for page up and page down. And I have a third switch that is just to turn this off entirely if I don't need it. So point is, I have wires now coming from somewhere else to headers on the circuit board. And at first I just ran them straight to the MCU because why wouldn't you? Did I mention I've learned a lot? So I was having a board review just a few days ago on Saturday with some of the patrons. Thank you guys again so much. one of the patrons commented, well, you could induce voltage onto the wire if there's any noise near the wires. They could act like little antennas, basically. And if I say anything wrong, I apologize, I'm still learning. At the time, I thought, well, there's nothing really at the Helm station that could do that. It's not like it's going to be in a noisy, like a machine room or something like that. But then one of them was like, but you have a handheld VHF antenna, or VHF radio. And I'm like, oh, shit, yes, I do. So I had to add some protection. So what I've got here is on the wire that comes in from the plug. Where did I just have that pot? There it is. So imagine this wire is basically like an antenna. And I take my handheld radio and I turn it on and it starts broadcasting at 6 watts. That's a fair bit of power that's now going to be passing over these wires. And when you pass a magnetic field over a conductor, you get voltage. That's how generators work. So I could suddenly have spikes of voltage coming down through this wire into the MCU. Now, I'm going to wrap the inside of the Helm with aluminum and that'll be grounded. So hopefully that'll deal with most of it. But I'm assuming that I have no protection, designed for worst case. This R20, the 10 kilowatt, oh good lord. The 10 kilo ohm resistor is just a standard pull-up resistor. What does that mean? I didn't know either. When you have a GPIO pin on if you've got an Arduino, if anyone's done an Arduino, you're already familiar with this. Not sending voltage to it doesn't mean that it's zero. It just means that it's floating. And pins don't like to be floating. They want to either be clearly high or clearly low. So the way you do this is you put a resistor. If it's a pulled down resistor, you put like a 10K resistor on the pin going to the ground. So when there's no other influence, if there was any voltage, if it wasn't exactly at 0 volts, it'll be pulled down by going through that resistor slowly. But the resistor is a high enough resistance that if I send a 5 volt signal or 3.3 volt signal towards that pin, some of it will bleed through the resistor, but it's a high enough value that the majority is going to go to the pin and pull it up to 1. So it's a clear 1. As soon as I pull the voltage off, because that ground resistor is there, any transient voltage or any leftover voltage gets sucked down to ground and the voltage drops back to 0, and now the GPIO has a clear 0 input. Pull-up resistor is exactly the opposite. It means that it's always pulling to the 3.3. If I say 5 volt or 3.3 volt, the STM32s are always 3.3 volts, but I do have some 5 volt devices and I just sometimes blurt them out backwards. I know which voltages are which. Apologies if I get them wrong when I'm talking. Anyways, back to it. What you're seeing here are what's called NetNames. And to anybody who's done circuit boards, this stuff is so 101, and I don't want to pretend like I sound like I know what I'm talking about. I barely do. But for folks like me who didn't know shite before starting this, it's some basics. So if you actually look at the MCU, everything goes to NetNames. So there's the I2C. So I have the serial data and the serial clock. So instead of actually running a trace, which would very quickly make this schematic impossible to read because there'd be wires going everywhere, I instead set it out to a net name. So board I2C, SDA, and wherever I want to use it, there it is. So board I2C, SDA, and SCL, serial data and serial clock. You can see these two memory chips have a wire tying them into the board I2C. This is a way of just saving me from having to manually run the wires everywhere. And this translates to creating an electrically complete circuit so that when you go to lay out the circuit board, it knows where all your connections have to be. So if anything's missing, it tells you, or if anything's connected the wrong way, it warns you. So you'll see on the plugs, so I have another DB9 connector, one for the serial so I can actually talk to the MCU and see the data coming and going. That one is a female header. I have a male header. The male header is going to be another DB9 that I can screw in and has the wires going off to the switches and the pots and whatnot. So you see here I have LCD page up in, just means it's going into the MCU, into the CPU, plug side. And then coming down here, I have LCD page up plug. So that tells it, this wire here, just pretend it goes all the way to that pin on the connector that goes to the physical switch. And then it does its doohickey stuff. And then on the other side, LCD page up in. That's a separate net, which then ties to the MCU, LCD page up in. This we go, right there. If you remember the IS31, it's got all of these CA1 through 9 and CB1 through 9. I always want to think anode and cathode, but it's A and B, and that's not what it is, because any one pin, actually, briefly, how does a Charlieplexer work? So trying to drive 144 LEDs with the fewest number of GPIO pins requires you to be creative. And there's different ways to do it, but the way the Charlieplexer does it is, it basically loops through, and on each sweep, it will take each pair of pins, so CA1 and actually let's look at one of these specifically. So CA1 and CA2 should go to the very first LED, which is the outer ring north position. So you can see how if CA1 is connected to ground, and then CA2 has a voltage sent to it, this LED comes on. So it'll drive that LED on for however long, however brightness, depending on how it's configured, and then it turns it off and it moves over to the next one. If I want to light up diode 1 and diode 2 at the same time, what it's going to actually, and this is simplified, is it is going to say, okay, CA1, pin CA1, you're now ground. It's going to go to CA2, you're now an anode, positive, and it's going to send voltage out. And then LED D1 lights up, but only for a moment. Then it switches over and turns on A3 and provides voltage. But before it does that, it has to stop providing voltage to CA2. Only at any one moment in time, only two pins are active. One is an anode, one is a cathode. One has the positive and one has the negative. But it does it goes through and sweeps so fast that persistence of vision, the reason why CRTs work and anything, if you've ever tried to record anything and it flickers, it's because it's using persistence of vision to make it look like it's a solid object. LEDs are fantastically famous for this. Because they're not on all the time. If you just take like a battery and a resistor and you plug it to an LED, it's just on and it's not flickering. So no matter what speed your camera is set to, it's never going to flicker on you. But when you're using PWM, pulse width modulation, to control the lights, you have to turn them on bright enough and then turn it off, do all of the others, come back to this one and turn it back on fast enough that your eyes don't notice. This is how Charlieplexers work. But this is the idea, is it would turn on CA3, then turn it off and turn on CA4, turn it off, turn on CA5, turn it off, turn on CA6, and go through the cycle. Once it's done with CA1, it now goes to CB1. CB1 becomes a ground, and it'll go through CB2 through 9, lighting them up in sequence, or not, depending if the LED is off or on. Or if you're dimming it, you only want it, say, 50% brightness. This is how the dimming function is going to work. The pulse, the period of time that the light is on, shrinks the dimmer the light you want. The dimmer you want the light to be. There we go. I'll go into more detail when I actually build this board. But you're getting kind of an idea of how the nets tie everything together, how to deal with the isolation, how to protect the GPIO pins, blah, blah, blah. All of that was for just this one board. And remember, that's where this started. I started this project thinking it was going to be a week or two. It's been 3 months. If you're wondering why I haven't been doing a lot of detailed videos lately, this is why. Okay, so let's take a look at what this PCB looks like. It's already been routed. So when you actually go to, and these are all 4-layer boards, meaning you have the outer copper, you have the inner copper, but then in between you have 2 more layers you can't see. The top one on all of my boards is going to be a ground layer. So if anything needs a ground, board ground. When I have multiple grounds, it's always the board ground. Ship ground and other isolations are their own ground planes, blah, blah, blah. Keep it simple, it's just a ground plane. Let me turn everything off, except, okay, so there's the bare circuit board looking from the top down. If I look at the top layer, here, if I'm looking at the physical circuit board, I can see the traces. I have one of these I can do this in. There you go. Yeah, you can see that on this. So this one is blue, but you see right there, for example, there's 2 really fat traces that you can see under the epoxy layer. I think it's epoxy, whatever they use to protect the conductor underneath. You can see all of the wires that have been laid out on the board. I have another one that I can show you as well, back at the LCD panel. So you see how you see the lighter shade of white? Those are all the traces. The darker shade is where the copper has been eaten away, and then you have the cover on the end, the green epoxy or whatever it is. So these wires here, you're going to see on the front of it. If I turn that off, see how there's the flood? It's almost all green. That's the ground wire. Now there's a few times where I had no choice. I couldn't put a trace on the outer sides, I had to use one of the inner layers to run a signal. You don't generally want to do that because if a trace is on either side and you have a problem and you need to cut it to break the circuit because you made a mistake, which I am certainly going to have mistakes on this, on the outer layers, I can just cut it with a knife to break it and then put a bodge wire to run it to the right place. You don't generally want to run logic traces on anything in the middle layers. You can see here, for example, see how that's the ground? And the ground has a couple of these pins coming off. I didn't have to run a wire to here because it just automatically connected it to this ground plane. So that is the ground plane. And then the next one is, I have another flood plane that is 3.3 volts. So in the same way that if I have a device that has a ground pin, which they all do, and that device also needs 3.3 volts, I don't have to go and run wires all around to provide the 3.3 volts. They just magically connect to that middle layer. Now, obviously, if I have a 5 volt or a 12 volt, or it's a 5 volt that is on a different network because of isolation, they can't connect to this. But it means most of the stuff will have a connection auto-magically and I don't have to run traces. Also, the ground one provides protection from noise. How? I don't know. I'm still learning. So that is the fill layer for providing voltage. And now this is the back of the circuit board. So if you flip the board over, you would see these traces. So when you start, I can't do it now. I kind of wish I had recorded this. I'm sorry, I was so in the learning curve I didn't turn anything on. But when you first start laying it out, you click on here and it brings all of the parts in, and that came from the schematic, they would just be dropped here. They're just dropped. Have fun, put it together. Some of the parts are going to be sticking out one side, some of the parts are sticking out the other on my board. The reason for that is I want the board's LEDs and LCD to be hidden by plexi. This is something else I haven't played with much yet, but continuing with the 1980s theme, I want to go for, I wonder if I can put a screenshot in without triggering copyright. I'm hopefully putting a picture here of the Helm console from Star Trek The Next Generation, the navigation Helm. So this was one of the boards I was going to do before I decided to make a PCB. That'll sit behind it so that you won't really see it until it lights up and then the light comes through. So the LEDs will be up against the underside, but then all of the logic parts and all the passive parts and the connectors and everything are going to be on the back side. That's why I'm doing things like this. I don't know which shade is going to look most 80s and still let the light through, so I've got 3 different shades of smoked plexiglass. I am so stoked to build the Helm console. Okay, but that's down the road. One of the other reasons I decided to keep going with this, even though I knew it was kind of, arguably, could I have made the boat move without this? Yes, I could have just gotten simple pots to run into the Kelly controllers and the boat would have moved. But to me, when the boat goes in the water, I need it for my sanity to be moving under my logic and my software. And I say my, acknowledging all of the amazing help that I've gotten. It's ours, but you know what I mean. I need to see the Helm light up the way I've seen it in my head for 3 years now and actually move the boat this way. So this is why I've prioritized doing all this PCB work. Once I realized the boat wasn't going into the water last year, well, this year, but during the summer, the season that went past, I kind of was like, all right, back off, take your time, do it right, make the circuit boards. Right, getting back to it. Once you have everything placed and you've got the wires connected all through them, there's something really annoying but also amazing. You run something called a DRC, a design rule check. And when you run this, please pretend you don't see the warnings. When you first lay it out, you have lots and lots of errors. Missing connections, things that short out other things. It throws all these error messages and you have to go through and you have to fine tune the design until all the errors go away. Once all the errors are gone, then you can print out something called Gerber files, which is what the companies who actually make the PCBs use to make the PCBs. But before we get to that, one of the things I love about, this is KiCAD by the way, KiCAD 9. I'm a beginner. I have no way of comparing it to other programs to say whether it's great compared to Altium or whatever, but it has done everything I needed, and I can't speak highly enough of the community. The KiCAD Discord, I don't think I've gone more than 30 minutes between asking a question and getting an answer. Fantastically active community, lots of videos out there. If you are like me and you want to learn PCB stuff and you're just getting started, understanding my experience and for what it's worth, I fully endorse it. Now, one of the things I really like is you can do, what is it, option 3? You can get 3D renders. How cool is this? But you can see how, what it's going to look like. You can't really move things around really easily. But, oh, wrong way. There we go. So you can see this is where, can I move the mouse? Because the on-screen display is going to be hiding it. But you can see these traces and you can see the little vias, which is where if a wire has to punch through and go a different direction on a different layer. And all the pinouts, and there's all of my LEDs. It was fun because I had to learn how to, because these LEDs weren't in the stock library, but it has a mechanism for being able to create your own parts, including in 3D. I didn't do the 3D animation. I was downloading the .stp or step files from the vendors. Almost all the vendors had 3D files for rendering their parts. You just have to put it together. And you can flip it around. Yes, I put a mermaid on it because of course I did. I bought it from an Etsy designer. I'm hoping at some point, a friend of mine's an artist, and she's really busy right now, but I'm hoping that before I make more of them, I'll get an actual custom mermaid on the silkscreen. You can see there's the IS31 chip. You can see all the wires coming off of it, all of the capacitors. These, something called decoupling capacitors. It's all stuff I've learned about. We'll go into details when I build the board. How many times have I said that? These cutouts are for the switches that will punch through to the front panel for page up, page down, turning the things on, dials and whatnot. There's the two memory bits there. Test points. So many test points. And this is one of the things that oh, wrong way. One of the pieces of advice wrong way. I got from the folks in the Discord was have test points so that you can clip your oscilloscope probes to when you're debugging your software. I don't know how to use an oscilloscope yet, but I'm going to learn. So much I'm going to learn. Oh, you notice how you've got thermal pads here. Let me zoom back out. Remember I showed you how I had the 12 volt to 5 volt and 5 volt to 3.3 volt? Those generate heat when they're working. I cannot tell you how tickled my nerd glands are at seeing this and knowing that I laid it out. If you've ever thought about making a circuit board and you have any claim to being a nerd, do it. Do it now, do it yesterday. There you go. There's one of the linear regulators. That's what the LR is. This generates a fair bit of heat. So in the same way that you would have a heat sink for like a CPU or something like that, having a big plot of copper on both sides with the through holes to help transfer some of the heat through. And these are like 1 millimeter holes. They'll be plugged with solder to help transfer the heat to the other side. So it basically acts like a couple of radiators to take the heat away because these are not super efficient. Switching power supplies are the most efficient, but they're much, much bigger and more complicated. And for the tiny little bit of current that I need at these various voltages, this was fine. Oh, N2K2. I can show you a fix. Okay, so see how that says N2K2? That should be N2K1. That's because at some point I deleted it and added a second one and it incremented the number. Where's the N2K? There it is, there it is, there it is. It's under here, so I have to hide those layers. There it is. Now that's wrong. So what I can do is come back to my design, come to here, change this to 1, save it, do my DRC checks, even though I know that's not going to break anything. No errors. So now I can go back to my PCB and I can click update from the schematic, update PCB, close, and now it's N2K1. So it's the first connector. Now, if I do the animation or the 3D again, sorry, I'm very excited and talking very fast because this shit is awesome. There you go, N2K1. It's that easy. If I had just seen somebody show me all of this 3 months ago and said, yeah, you'll be doing this in 3 months, I'd be like, you have too much faith in me. But it's really not that hard. So anyways, I have a whole bunch of power supply protection stuff. Probably the majority of the cost and component count has gone into power protection. If you recall back when I was, the last video I did a while ago where I was using all of the wires on the breadboard to try to control the motors and it was not behaving very predictably, almost certainly it's because I didn't have a lot of this power stuff and signal protection stuff and it was just, there was noise everywhere. Between making a board work and making a board work well is a couple of weeks versus 3 months worth of work. That is the biggest lesson I've taken over this lately. So now when you want to take nice pretty pictures, it's just an M1 Mac, it's nothing fancy, but you can even do ray tracing to make it like have shadows and stuff. Voila! It's off kilter, but you can see now it's got shadows and it's prettier looking. Is that useful? No. Does it make me happy? Oh yes. Okay, So that was just kind of showing the process of what I've been doing for the last 3 months. In total, I now have 4 boards, and I want to tell you briefly what those 4 boards are, and that'll be it for this video. And then I've got some other stuff I need to do, but all of the parts are going to be on order, and I'm going to make videos as I assemble each board and go into more detail, like I said. So let's look at the other ones. So that was the CANbus rows. Let's look at the MCU, the main control unit. This is kind of like the brain, the motherboard of the boat. This is going to replace what I had built on the breadboard to control the motors earlier. That's effectively what this is, just ridiculously better than I had it before. So the motor controllers, where's one? The Kelly motor controllers that I ordered, I paid for the CANbus option. The CANbus option, and this is not NMEA 2000, this is actual CANbus. The key thing is that it'll allow me to get things like motor RPM, the temperature of the motor, temperature of the controller, and a whole bunch of other data that I very much want to have. So I have on this board, which is using a different MCU, which is going to be so fun to solder. It is the STM32 G474RET. That's Golf 474 Romeo Echo Tango. Links to all of the key parts I'll put in the description when I make the video. This is a much more high-performance chip, uses more power, so it's one of the reasons I'm using it only once. Costs more, which is about 4 to 5 times more expensive than the MCU I'm using on the other boards. But that's, in the grand scheme of things, $8 difference is not a huge difference. The main reason I'm not using it across the board is because I want the power savings of the smaller chips. This one has, the key thing about this one is that instead of having 1 CANbus connection, it has 3. So I've got my NMEA 2000, which you saw on the previous board, and then 2 more CAN ports, one for the 10 kilowatt controller and one for the 5 kilowatt controller. All 3 of those have to have their own isolation. I have 4 different isolated power buses on this board. So much of what you see here is the connection to the NMEA 2000, which gives me the data connection and the power for the board, which then goes through the same 12 volt to 5 volt isolated, 12 volt to 5 volt isolated, 12 volt to 5 volt non-isolated, and 5 volt to 3.3 volt. So I have these 2 more isolated planes for the 2 motor controllers. First I have the CAN connections, and to actually communicate logically, pressing the foot switch, choosing high speed, mid speed, low speed. So those digital signals have to go through their own isolators. And then on the other side, I have to have a way of sending a 0 to 5 volt signal to the motor controllers to signal how strong I want the regen and how fast I want the throttle. So those go through their own DACs, which are themselves isolated. So I have the digital signal that is coming out of the main control unit, the CPU, the STM32. That digital signal goes into the MCP 4726, which converts it to an actual voltage, which gets sent down to the Kelly motor controllers over their dedicated pins. So all of the motor control and CAN connection are isolated per motor controller. I have the same dual memory configuration I talked about. Here, this is going to allow me to do things like record what did I want the throttle at, so that if I suddenly lose the throttle input, it goes to 0, for example, I know what I was sending to the throttle to hold it constant, even if then the board reboots. When it reboots, if it doesn't have real throttle data, it can go and read it out of the memory and continue to feed the previous throttle to the controller, even through a reboot. That's the kind of stuff I want to be able to use for the memory. And then the redundancy. Do I need the redundancy? No, these chips are super reliable, but it just tickles me pink, and I had lots of space for them, and I wanted to. I love redundancy. I have another LCD. I'm gonna have a whole bunch of LCDs on these things. 7-segment displays. What am I going to use this for? I'm honestly not sure, but I had to have them. How can anything be 80s themed and not have 7-segment displays? I will probably use them for showing things like how many kilowatts are going into the motor that's active pushing the boat, or if I'm under regen, how many kilowatts are coming out of the, or watts are coming out of the motor into the batteries. I could also do things like track RPM, blah, blah, blah. They're there. I have 6 digits. I will use them for things. This is how I did the isolated control switching. So remember I was saying earlier that pressing the foot switch, go high, low. This is where I was taking the data coming from the motors, or coming from the controller, and sending it to the motors with isolation. And here I'm using opto-isolators. An opto-isolator is a tiny, tiny little wee chip. Where's one? Hello. Even smaller than this. It's only got 3 legs. This has got more than 3 legs. It is basically a little ultraviolet LED on one side and a solar panel, a transistor, on the other side. So if I want to send a, for example, press the foot switch, it lights up the LED, and that energy coming off the LED hits the diode on the other side, the transistor on the other side, and allows voltage to pass and closes the switch with no electrical connection. It's purely done by light. Tell me that isn't cool. I also have the throttle controls. So I have 2 LEDs on either side that are going to be lit up when the motor is in neutral. And then I have 20 LEDs for the forward and 20 LEDs for reverse. What this does is, between 0 and 100, I have 1 LED for every 5%. This is very similar to how I'm going to do the Compass Rose. The Compass Rose has 72 LEDs for 360 degrees, meaning I have 1 LED for every 5 degrees of movement. That's too granular. So the way I'm going to indicate the space in between is that, using the compass as an example, let's say that I'm exactly on 90 degrees heading east. So the 90-degree LED is 100% lit and both LEDs on either side are dark. But now let's say I go to 91 degrees. What I'll do is I'll dim the 90 LED to 80% and I'll turn on the 95 LED to 20%. And that relative brightness between the two will tell me it's 91. 92 will be 60-40, then 40-60, and then 20-80, and then 0-100. And that'll give me my 1 degree resolution between my 2 5-degree LEDs. Similar for the throttle. If I'm at, 27% throttle, it'll be 25 LED at 60% brightness, and the 30% LED at 40% brightness. So that is the throttle. These are all the GPIO pin protection, which we talked about before. Look at all of these D-sub connectors. I have stacks of D-subs. Anybody who used computers back in the 80s knows exactly what I'm talking about. The old printer ports were DB25, so 2 rows, 25 pins total, 12 pins and 13 pins offset like a W kind of shape. 9-pin and 15-pin. 15-pin were used for joystick and MIDI, 9-pin was usually used for serial. For those of you who used to use dial-up modems, all of those style pins. Now, I made sure that the parts I selected were all tinned, like everything else on the boat. The housings, the metal, the D-sub part of it is going to be tinned, and the pins themselves are gold. Is it still going to corrode? It's a boat. Of course it is. I'll have spares. All of that I'll go into detail when I start making the boards, but I have acknowledged this. It's not going to be your cheap... I'm not getting just like the cheapest connectors that everyone saw rust out back in the day. I'm going to have LEDs all over. I bought a bag of 500 of these rectangular LEDs, and my bill of material tells me that I need about 750. I'm going to be buying another bag of 500. I'm going to have 1,000 of these LEDs. It's ridiculous. They switch, for example, to go high speed, neutral, or low speed, or middle speed or low speed for the 10 kilowatt motor. There'll be a switch that has a ground and then high speed and low speed, neither being selected being medium speed. And then I've got the cathode and anode for the LED to say which motor, or each motor, what speed is it set to, high speed, mid speed, low speed. So I've got that's the enable pin, which goes to the foot switch. And then I've got connectors for all of the LEDs. And the reason I'm doing this is the LEDs have to be set at the, I'm going to do 3D printed jigs that's going to mount them at the behind the plexiglass. So they have to be off the main board, which is why they have the wires going to the connectors. The CANbus connectors, so the motor controllers have these types of connectors. I've been calling them Deutsch connectors, but I don't think they're actually Deutsch connectors, whatever they actually are. These, I'm actually really tempted to cut them off and put them on to something more skookum, but I'll probably just go into the boat with these as they are. But the other side that came, if you remember in that video when I was getting the motor spinning for the first time, it had the opposite end connectors that just went to flying leads that I ran into the board. Those will go to the DB9 connectors now. I've also been doing work on the motor controllers. God, I haven't been making a lot of videos showing the details lately, but that's only because I've been doing a lot of research, which is boring video content. I have so much coming. So then I got the 2 DB15 female, I got 2 DB15 male, And then I've got the stacked DB9 female for all of the connectors. Like, there it is. If you really want to see what all the pins are, go to the GitHub, or it's going to be on GitHub for now, which is going to be super helpful to a lot of people. Anyone who are patrons, I have a Google Drive where I've actually shared all of the plotted out PDFs and all the stuff I've got it on a Google Drive, but I'm going to leave that for the patrons. The GitHub is there for those who are not patrons. Not because I don't want the participation of regular people, but these patrons, man, I cannot tell you how much they've been helping me. I need to do something special for them, so I got to keep some stuff for them. So all of these various input-output connections need to have the signal protection like I talked about earlier in case I induce voltage onto the wires, and that's what all of this is. That is the most complex board. Oh, and then I have an e-stop. The e-stop button I found is ridiculous. Yeah, I gotta find it. It's too cool not to show it. Check this thing out. It is so 1980s badass. I cannot wait. It's expensive, but come on, a girl has to live now and then. Look at it. Look how cool that is. That's my e-stop switch. Now, the problem is that this e-stop switch has to stop both motors. I'm only going to be driving one motor at a time, and I thought, well, if that's the case, I could just run it into the control unit, but one of the patrons said, you know what, the e-stop really should bypass your board in case your board's acting up and cut the motors directly. So this e-stop it's got two circuits through it, plus a third one for the LED. One circuit is going to go to the foot switch for the 10 kilowatt, and the other one's going to go to the foot switch for the 5 kilowatt. If either of those are interrupted, the motor shuts down. Now, that's important because one of the other many things that have happened in the last little while that I have not yet made videos for is I traded my diesel engine. It's gone. I traded it for a 1-cylinder Yanmar. It's a 5 horsepower. It's tiny. It's so itty bitty. That is going to, the plan currently in my head, I'm going to have that set up to the 10 kilowatt motor, maybe the 5 kilowatt motor, to be determined. Point is, if I run low on batteries and I still need to move, which is pretty much the only reason I would run the generator anyway, I want to be able to have one motor acting as a generator while the other motor is actually propulsing the boat. And I don't want to have a big motor that's going to take up a lot of space. I don't need the inverter component. I just need something that outputs a stable voltage to charge the batteries. So, thanks me, you've already got a generator alternator in the form of... I already have a generator or an alternator. It's my motor. Why buy an alternator? It's a waste of space. It's a waste of money. And this puts out the right voltage to charge my batteries anyway. So I could be in a situation where one motor is being used to push while the other motor is being used to convert electricity coming from the diesel into electricity. So having the e-stop cut the foot switch to both motors means that no matter what configuration the boat is currently acting in, it shuts it all down. It's glowing red and it's black. I love it so much. And you can see there just a moment ago, last purchased. I placed the order today for all of the parts. I literally finished this yesterday. So this e-stop switch logic, it interrupts the foot switch, which is the most important thing. But if the control board is still working, I need to know that the user has pressed the e-stop switch. If that happens, I want the main controller, if it's still working, to know that the user has hit the e-stop. So when the e-stop button is pressed, as well as on top of breaking the connection to the foot switch to the two Kelly controllers, I need to signal a message to the MCU so that it knows that the user has gone into e-stop and it can safe everything. But there has to be a flip to that. If the MCU wants to be the one that triggers an emergency stop for whatever reason, something's overheating, for example, I want the MCU to be able to send a signal that cuts the foot switch for both motor controllers. So this little circuit here does all of that. So with all of that, we get this PCB, which is a lot more complicated. Now, there's a lot of dead space on this board. It is not optimized, I know. I have redesigned this board multiple times. It's good enough. At some point, I'm probably going to sit down and redo this all again because I'm going to learn so much between now and when the boat's in the water. I'll make a more efficient board then. Without going through all of the details, this is what it looks like. So this is going to be the side that's facing the plexiglass. You can see the 7-segment display, the LCD, and there's the throttle. And at the top, there's going to be, am I running in remote control, starboard throttle, or port throttle? And because I want everything to be field repairable when I'm underway, which is one of the big reasons I wanted to do all of this stuff from scratch myself, because there was no product on the market where how the board works was shared with the consumer. You couldn't fix it. It was all just black box. The single biggest reason for doing all of this is field repairability. And the reason why I'm hoping other sailors might be interested in working on this project and building on it and using it themselves is for the same reason. If something breaks and you're in the middle of nowhere, you can't get to an authorized Torqeedo or Ocean Volt place to get it fixed. You have to be able to fix it yourself. In that ethos, I have printed right on the silk screen what every plug is and what every wire is. All of the active components are labeled with what the component is. If it has I2C addresses, like the memory, it tells you what address it's all at. And then here is all of the D-sub connectors. Tell me that doesn't look so 80s industrial. Whoops. Let's zoom in. I do not like the scroll wheel on the Magic Mouse. Now, one thing I didn't talk about was relays. I have a separate relay board, which we're going to look at in a second, but if the NMEA 2000 bus went down for some reason, I wanted to be able to control the blower fan for the engine bay, and I wanted to be able to control the pump for the liquid cooling of the motor and the controller myself. So I have a couple of automotive 12-volt switches with a big protection diode so that I can run 16 amp inductive loads through these relays. The same ring terminals that I'm using for all of the breakers will fit onto this. So I can take the wire that goes to the breaker for the blower or to the pump, and I just run it through this MCU as well. Now what I'll be able to do is, because I've got the temperature data coming in off the CANbus for the Kelly controller and the motors, I'll be able to say, don't run the pump until it actually warms up. When it's warm enough, go ahead and turn on the pump. And once it cools off, turn the pump off again. I have because this one has the more advanced MCU, there's a full-on JTAG header. So anybody who does any kind of software development or firmware development, you can plug into this and it's fully reconfigurable. I've done everything I can to make this as hackable as possible. There's also a couple of switches for boot and reset on the STM. This is on all of the boards. So you can boot up and yeah. Okay, so that is the big board. I have two more boards I want to show you, and then we're going to done, and I'm going to get on to finishing the battery box. So the next one is the battery display. So I've got the 5 48-volt batteries, and I'm going to have 2 12-volt batteries. And I wanted to be able to see the state of charge of the individual packs, and then the average remaining of them. So I might have like one at, say 80% state of charge, another one at 40% state of charge. The average is going to be 60% state of charge. That's really simplistic, but that's why you see 3 rows of LEDs for the 12-volt. I have pack 1, pack 2, and then the average of the 2. And then same idea, I have 48-volt average, and then the 5 individual packs. These are only 10 LEDs. Each LED indicates, 0, 10, 20, 30, 40%, so I've got like a 10% gap between them. That same LED fading trick I'm gonna do, except instead of doing, 180, 60, 20, it'll be 190, 80, 70, 60, 10 steps, or 10 steps, whatever. You get the point. One of the other things that's important is this also has another LCD. The ABYC requires, as part of, I think it's E13, the electric propulsion, you have to be able to show our estimated range and estimated runtime remaining at, depending on what the throttle position is. So I'll probably look over the last 5 minutes, 10 minutes, 15 minutes, whatever I find to be useful, and say, what's the average consumption been and how fast have I traveled in that time? And I'll be able to display on the LCD how much more time and how much more distance I should get if the conditions remain the same. Anybody with an electric car that has the range estimate, it's the same logic. There's my memory chips again. This is a pretty simple board because it's just the battery display. It has the same, where's the programming header? Oh, there it is. There's a programming header. There's the serial port, my voltage regulation, and this is the C0 MCU again. Really, really simple, very little input, so there's just a few GPIO pin protection. Don't get so excited you can't talk, Maddie. And here is what it looks like. So you can see, if I can zoom in, on the silk screen, you can see that it shows the 12-volt here. There's the 51.2 volt. I called it 48 volt before, but I actually showed them on the silk screen as their real nominal voltages. And the LCD. And then there's those cutouts for the switches, the page up, page down to change what's being displayed and turn the display on and off. And the last one is also very simple, but also I think one of the ones I'm more excited to play with. I mean, I'm excited to play with all of them, but you know what I mean. Digital switching. So what this is here, I want to be able to control when I have the steaming light on, the navigation lights, the deck light, and the anchor light. I also want to be able to control things like, what are some of the other things I'm going to run through this? The pump and the blower are going through the MCU. I had a bunch of ideas of what I'm going to run through this, but right now the nav lights are the main one I'm thinking of because those are what have to work in order for the boat to go in the water. Normally, what you do is just, if it gets dark, you run in and you flip the switch and you turn on the nav lights. Or if you're turning on the engine, you go in and you flip on the steaming light. Or if you drop the hook, you go and flip the switch for the anchor light and you turn off the other ones. Which is fine, it's dandy, it would work, and I could have done that. It's what I was going to do, just bog standard, if I got the boat in the water this year. But I didn't, and so I'm going to have a relay board with 9 relays, but they are latching relays. So the relay that I'm using on the main control unit is just a bog standard automotive relay. When you send power to the coil, it closes the connection and power flows through, and when you're done, you release the coil and it breaks the connection. Done and simple. But the downside to that is it means that the coil has to be powered and consuming electricity the entire time you want the relay closed. For the cooling fan and for the pump, I'm not too terribly concerned about that. If I'm in a situation where those have to turn on, the amount of power used by the relay is an infinitesimal rounding error compared to how much battery power I'm using to actually propulse the boat. The lights, on the other hand, could theoretically be turned on for 10, 12 hours at a time. So there's a little bit of coil voltage, it adds up. So I wanted to use latching relays. A latching relay is you signal it for just a period of time and it changes state, set it. That closes the circuit. When I want to break the circuit, I have to send a separate signal, charge the opposite coil, and it unsets it. So it's more energy efficient because the coils only need power for a very short period of time. So this has 9 of those. It has an LCD. Does it have an LCD? No, it does not have an LCD. This is the only one without an LCD, but this is another example of why I wanted to have built-in non-volatile memory on the boards. If this board reboots for some reason, I want to have in memory what the user last commanded the states of the relays to be. I wanted to make this thing draw as little power as possible because this is generally never going to be looked at. So there's going to be LEDs to show whether each individual relay is open or closed, but they're all going to be off by default. If you hit the momentary switch, it'll turn on the status LEDs for say 10 seconds, 15 seconds, and then turn them back off again. The others will turn the switch down and hold it on so the lights will stay on as long as you want them to be. It does have the Charlieplexer. It's way overkill for this board, but I have the code. Well, I will have the code for all the other boards, so I just decided to use it, but it has a shutdown pin. So when you flip that switch and say, hey, I want to see the status of the LEDs, it actually goes and turns on the Charlieplexer chip long enough to show the LEDs for however long the user wants. And then when it times out, it shuts the chip down. So it reduces the drops. That chip, when it's not driving LEDs, but it's turned on, it's still drawing milliamps. When the chip is commanded off, it's drawing microamps. Now again, consider on a 3-week passage, milliamps add up to amps, and amps turn up to noticeable watts. So everything is about energy efficiency here. I got all the other bog standard stuff that you've seen before, so we can jump directly, show the circuit. It's narrow, it's like a stick of gum. Well, a really big stick of gum. Now, inductive loads. An inductive load is things like pumps and motors, anything that where you have a big coil of wire. When they break, when you cut the power to them, the magnetic field that was in the wire, much similar or very similar to the problem you have with alternators. If you disconnect the load suddenly, the magnetic field starts to collapse, and as that magnetic field collapses, the energy is being converted into voltage. So when the inductive load is disconnected and that voltage starts to climb, it can arc through and start to damage things. To prevent this, you use diodes, fairly chunky diodes. Can I get a good view of one? There you go. So these big diodes, they only work if you connect the load in the right order. So the relay itself, it's just breaking the wire. It doesn't really matter with a standard circuit breaker which way you put the wires. It's a switch. It's dumb. And if I did not have these protection diodes so that I could handle inductive loads, it wouldn't matter which way I connected the wires either. But because these diodes are here, it does matter. I have to make sure that I go from power source to load in the right order. So I have the silk screens for in and out. So in from the power, out to the load. There's the TBS diodes, there's the latching relays, and there's the indicator LEDs. I don't know exactly how I'm going to work these. I put 3 on, so I'm thinking I might light up either side with the middle light off if the circuit is open, and connect all 3, or maybe have the center one pulsing if there's power going through it. I don't know yet. That is art that I will deal with later. But I have 9 of these. I'm going to have one of them for driving all of the exterior stuff, lights, cameras, whatever I might want to drive down the road. And then I'm going to have a second one for all of the interior lights. Okay, that is that. This has been a whole lot of talking, but after 3 months of constant work, I really wanted to show you what I was doing, and I didn't want to wait until I actually started assembling everything. Also, this gives context to those coming videos. So, I'm sorry there wasn't a whole lot of visual interest in this one. Hopefully the screen record was interesting enough, but this has been a huge, huge, huge investment of time into this project, and I am so stoked. I've been working on a whole bunch of other projects. My mass has been picked up. I have so many videos I'm going to have for you guys in the next little bit. Now that this massive consumption of time is hopefully mostly behind me, I'm going to get back to more regular videos. I'm not promising, like I've never promised really schedules, but yeah, I got a whole lot of stuff coming. So if you like this kind of stuff, do the YouTube thingamajigs, and I'm the Digital Mermaid. I am going to go rest now. Bye! And as the voltage starts to climb, as the